AP Calculus BC, Unit 5, Day 2, this lesson. So we're going to actually learn something new today. Well, actually, it's like an Algebra 1 kind of skill, but maybe you haven't learned it before. So now, we could just try this one. You know, our technique so far, a lot of times the denominator is a good U. So du equals 6x to the 5th plus 4x cubed dx. And this looks like it's going to work. Like we could take a 2 out to get what's on the top, right? I'll give you that. So we're going to divide by 2. Don't want the 2. This is going to be 1/2 integral of du over u. So that's going to be 1/2 natural log of the absolute value of u plus c 1/2 natural log of the absolute value of x to the 6th plus x to the 4th plus 2 plus c. Can we write it without the absolute values? Yes, we can, because that will always be positive no matter what you plug in, zeros, negatives, positives. So we're going to rewrite it without absolute values. You should put parentheses around it, so it's not really lesson writing, but it is simplified. Anyways, hey, that worked. But here's another one. Let's try this one. Let's go u equals x squared minus 2x minus 3. Du equals 2x minus 2 dx. Can we make this give us 5x minus 3? No. So that's not going to work. Usually if that doesn't work, then we start getting creative looking for inverse trig and stuff like that, but that's not going to work here either. So what we're going to do is we're going to try and break this fraction up into something that we can integrate. We can't just distribute the trinomial into the several ones. We could do that, but that wouldn't make it better. So what we're going to do is we're going to factor the bottom. And so this works if we can factor it. So minus 3 plus 1, that's right. And so we're going to actually be able to figure out a way of splitting this up into something, a number over x minus 3 and a number over x plus 1. And if we can do that, this can be easy to integrate. So how do we do that? It's called partial fractions. And this is the algebra technique I was referring to. So it really is an algebra technique. I don't remember ever teaching it when I taught algebra, or even algebra 2. But it's a simple algebra technique that we'll use to change this so we can factor it. So here's the way it works. So we're going to take a break from the calculus. We're going to say, all right, well that's the original fraction, and we want to somehow make it equal to a over x plus 3 equals b over x plus 1. I'm telling you, we should be able to do it. So one thing we're going to do is we're going to get rid of all the fractions by multiplying through by the least common denominator. And when we do that, these cancel out. So we get 5x minus 3. Over here, we distribute it. So here, the x minus 3's cancel out, but you still have an x plus 1 in the top. Here, the x plus 1's cancel, but you still have an x minus 3. And so that's what we do first. Now, what we could do is we could go ahead and distribute this ax plus a plus bx minus 3b. And what should be true is that all the x's over here should equal all the x's over here. So let's group the x's on the left-hand side and the non-x's. So let's group the x's. There's an a plus b times x. And then the other terms are a minus 3b. So we're kind of rearranging things. And what should be true is that this should equal 5, right? You have something x on this side, something x is both be 5x. So that gives you one equation, 5 equals a plus b. We're really trying to create a system of equations. And then this number should equal that number, right? Then it's just the number part. So negative 3 equals a minus 3b. And so now we have a system of equations. and then you guys should be able to solve it. Substitution. Linear combination works well here because they both have A's and B terms. So I'm going to use that. If I subtract this from the other equation, I get minus 5 minus A minus B. And I do this to get rid of one of the letters. So it just seemed like easy to get rid of the A's. You can get rid of the B's first if you want. So we have negative 8 equals negative 4B. And we solve for B, we get B equals 2. And then we could solve for A by plugging this back into either equation. I think this one seems the easiest. And so we get A plus 2 and A equals 3. So that's called partial fractions. We're splitting the fraction out. Now, once we do that, we could rewrite a problem, 5x minus 3 over x squared minus 2x minus 3 dx is really the same thing as 3 over x minus 3. So you got to make sure you put it the right one. Plus 2, and there should be dx here, plus 2 over x plus 1. And I'm going to separate them in separate integrals just because I am going to integrate them separately. So this is going to be 3 natural log of the absolute value of x minus 3. And this is going to be 2 natural log of the absolute value of x plus 1. You need the absolute values there. You need plus c. So this is the answer, but I'm just telling you that the answers are usually going to be a little more combined and simplified using log rules. So log rules, you'd have to bring these numbers in first, and then you could add these. So you can't add them, you can't combine them together with addition and subtraction unless they don't have coefficients front. So it's going to be natural log of x minus 3 cubed times absolute value of x plus 1 squared. Right? That's the log rules. And we could write that a little nicer because we don't need the absolute values around the x plus 1 anymore because it's going to come out positive no matter what if you square it, right? You still need them here. That would change the answer. So that seems like the most simplified answer. Now, there's some restrictions for this to work. Okay, for this to work, the degree of the top, the numerator, has to be less than the degree of the bottom, the denominator. Otherwise, we have a different technique to use first. So the degree of the bottom has to be, or the degree of the top has to be less than the degree of the bottom. So this is degree 1, this is degree 2, highest exponent. It works. If it were the other way around, upside down, couldn't do it. Also, the denominator has to be factorable. Or you could use a quadratic formula, or you could use synthetic division. So you got to be able to separate the factors. I mean, they could be ugly, and that's where quadratic formula comes in. Now, that was a lot of work. And so I'm going to show you a trick to streamline it. Okay? So we don't have to set up the system of equations every time. So I'm going to show you, it's called the Heaviside approach, and it's named after this guy, Oliver Heaviside. That was his name. Sometimes people call it the cover-up method. I'll probably usually refer to it as the Heaviside approach. You don't need to remember the name of it to use it. So I'm going to do the same problem, but quicker. So we're going to start with this fraction. I'm not concerned about the integrals. That's an easy thing afterwards. I'm just trying to do the new stuff. So we're going to set it equal to a over x minus 3 plus b over x plus 1. And it doesn't really matter which one you put over which one, but you just need to be consistent. Your answers will come out the same, but they'll be assigned to different letters if you set up with different letters or different places than someone else's. Now, where do you know the answer is 3 over x minus 3 plus 2 over x plus 1? I guess I shouldn't write that yet, but this is the same problem we did in the front. So this is what we're going to do. I'm going to kind of show you an in-between step that we usually won't write. So what we would do is we could put this all, I mean, this is essentially what we did. We gave them least common denominator, right? By multiplying through by the least common denominator. And so we just got 5x minus 3 equals ax plus 1, right? Plus bx minus 3. This is what we got in the front. And then we did all this crazy work. Well, this is easier. Why don't we pick a value of x that will make one of these disappear? And it doesn't matter which one. Sometimes it will. But, you could be like, well, let's get rid of the a's. So let's plug a -1 in. Okay? And then that will give you 0 times a, which goes away. Now, whatever we plug in one place, we got to plug in everywhere else. So that would give you -5 minus 3 is -8 equals -4b, b equals 2. Same answer. Super quick. So the technique here is pick an x value. So the coefficient of, in this case, we said of a is 0. Then do the same for b. Right? You can do b first and then a. So they call it Heaviside approach because that's the name of the guy. The cover-up method, it's almost like you're getting rid of that and then doing what's left, right? You're making that go away. So next time, I'm going to rewrite it, but in the future, we'll just put all this work on one of them. I just want to make it super clear first. I don't want to get too messy. So this time, or even to start with, let's plug 3 in for x's. So wherever we see an x, plug 3, and then that term goes away. And we get 15 minus 3 is 12 equals 4a. Divide both sides by 4. A equals 3. Right? Same answers, way faster. We get the same thing. Okay? Now, in the homework, there will be some problems where all you're doing is just practicing the partial fractions without any calculus involved. So this partial fraction thing, it's not a calculus technique. We're going to use it on calculus problems that we really need it, and it's possible this is the first time you've seen it. I want you guys to see if you can try this problem. So pause the video, try it, and the more of these you do, the better you're going to get. This one you can actually integrate after you split it up. Try and do it the faster way, okay? And then there's a couple special cases we need to talk about after that. So go ahead and pause the video and see if you can do it. Okay, I'm going to assume you did it. So we got to factor this first. It's going to be -2 minus 4. So one of them we're going to put over -2, and the other one we're going to put over -4. It doesn't matter which letter, which one we do first. You just need to be consistent with your work. And then we're going to integrate, right? So that's the plan. So the Heaviside approach says, all right, let's multiply through by the least common denominator, and you just get the numerator 2x plus 5 equals a x minus 4 plus b x minus 2. And then says, okay, well, let's get rid of one of these. You want to get rid of a first or b first? It doesn't really matter. Let me get rid of b first. Put 2 in, right? And so then that would be 4 plus 5 is 9 equals -2a. So a equals -9 halves. And then what we could do next is we say, well, let's plug 4 in where we did all the 2. So I'm going to cross them out. And this time that goes away and we get 13 equals 2b. So b equals 13 halves. So that's the new work. So now I'm going to rewrite it. Now, honestly, usually when I rewrite it, I just put this number out in front because it's just a constant. And I feel like it's less confusing to me if I just put it in front. -9 halves dx over x minus 2 plus 13 halves dx over x minus 4. That's how I like to do it. Break it up, put the coefficients in front. So now we're going to integrate -9 halves, natural log the absolute value of x minus 2, absolute values, plus 13 halves, natural log the absolute value of x minus 4, absolute values, plus c. Now that's an answer, but I guarantee when you check your answers in the book, and often if you're picking answers from multiple choice problems, they're not going to look like this. They're going to combine them all up. So let's practice that. I'm requiring it for your guys' test. So what we do is bring these in as exponents, right? And then we would have natural log of x minus 2 to the negative 9 halves times absolute value of x minus 4 to the 13 halves. Right, so that's all inside of a natural log, two separate absolute values. And then we could rewrite this. So this will end up in the denominator. So it's going to be x minus 4 to the 13 halves over x minus 2 to the 9 halves plus c. So we could write it like that. We could possibly take it further, or sometimes you're at the mercy of multiple choice answers. These are both square roots, so it could just be one big square root of, x minus 4 to the 13th power over x minus 2 to the 9th power absolute value inside plus c. I mean, that's the same thing. That's possibly a little nicer. You just got to be able to, get used to combining them. I'm going to want at least this. Okay, absolute values don't go away this time. If they had even exponent, sure. Now, there's a couple special cases. What happens when you get the same root twice? Okay, so let's act like we're going to do this problem. So if we factor this, it's going to be x minus 3, x minus 3. So this is called a repeated root because the root x minus 3 is repeated. And so this is the way you do it. You do a over x minus 3, and then you do b over, and I mean, your first instinct might be to do it like this, but that's not going to end up working. Everything's going to go away. You're not going to get anywhere. So for one of them, you need to square it. It's x minus 3 squared, right? So one of them you just put it first power. One of them you do it to the second power. So that's the special thing you got to do, okay? Now, some other weird things are going to happen. We're going to multiply through by the least common denominator, so you're going to get x plus 2 on the left, like normal. You can get a, x minus 3. This one will have an x minus 3 plus b. Now, shoot. Well, how do we get rid of the b? We can't get rid of the b this time. I mean, we could get rid of the a. Why don't we just start with that? Let's get rid of the a. So usually you can do a or b. It doesn't matter. Came on the same. This time you only can get rid of a. So 5 equals b. So we got b. Okay, but how do we get rid of b if we want to find a? Well, here's the deal. We're going to plug this in for b. And we could use this technique on the other problems. It's just unnecessarily adds a little more difficulty. The getting rid of one, getting rid of the other, that's the quickest, fastest way. This time we can't get rid of b, so we got to find b first and then plug it in. So this equation is x plus 2 equals a x minus 3 plus 5. That's what it is now. So instead of trying to get rid of b, we just put the number in for it. And now we plug in any value for x that you want other than 3, because we want to solve for a. So any value of x should work. I personally like to pick, you can pick 0, but I personally like to pick a value that'll make this 1. So I would pick 4. That'd be my favorite choice. And then you get 6 equals 1a plus 5. And then you solve for a equals 1. I just feel like it works out a little cleaner. So here's the deal. Add this note. Plug. So we have to get rid of a first and find b, and then plug it in, right? And then we plug anything in for x to get a, but not x equals 3. That would not work this time, right? I thought x equals 4 was nice. But you can plug anything. Just to illustrate, like we could plug 0 in and it would be 2 equals negative 3a plus 5. And then you get negative 3 equals negative 3a. And then you get a equals 1. Okay, same answer, right? I just think it was easier to plug something in that made that a positive 1 because it was less work, less steps. So the new integral is going to be a is 1, so that's going to be dx over x minus 3. B is 5, which I'd put out in front. Now, you got to check this out, though. This one's going to be natural log. right? Let's keep going. Let's finish it. This one's going to be natural log of the absolute value of x minus 3. This is not going to be natural log. This is power rule. This is x minus 3, then negative 2. So it's going to be plus 5. You're going to bump it up 1, right? Reverse power rule, and then divide by the new exponent, plus c. So then your final answer is natural log of the absolute value of x minus 3 minus 5 over x minus 3 plus c. I don't want negative exponents for final answers. You do need to leave the absolute values. So that repeated root 1, where we put it, that doesn't give you a log anymore. Logs usually come up on these. Okay, so that's a repeated factor. That's the strategy for that. Special case. And then the other thing we said on the front is that we can only use this when the degree of the top is smaller than the bottom. So if they're equal or the top's bigger, if the degree of the numerator is greater than or equal to, then we can't use this approach with the partial fractions. Now we might later in the problem, but what we first need to do is use long division, okay? So it's like synthetic division, but synthetic division is for special cases. And so let's see, phone is ringing. Okay, so we're going to use long division. So 2x cubed plus 5x squared plus 2x plus 6. If there are any missing terms, you need to put a 0 for that term there. It just makes it easier, including the denominator. So x squared plus 0x plus 1. So any missing degrees I would put there. So the first thing you're doing, it's kind of like regular long division. You know, when you do regular long division, it's like 93 divided by 8. And you say, well, how many times is 8 going to 9 one time? And you multiply it, and then you subtract. And then you say, well, how many times is 8 going to 13? Once, and you multiply it, and you subtract. And this is the remainder, right? Similar idea. So you say, okay, well, how many times does x squared go to 2x cubed? I'm like, oh, well, that would be 2x. Okay, and then so then you multiply it times all of this, and you get 2x cubed plus 0x squared plus 2x. And that's why you want to put any missing terms, so they all line up really nice. And then you're going to subtract it. You guys subtract each of these. These should go away if you pick the right number. This is going to be 5x squared, and then this is going to be 0x. So then, just like over here, you drop the next term down instead of the next digit, and you do the same thing. You say, well, how many times does x squared go into 5x squared? And you say, well, that's 5 plus 5. Then you multiply, and that would be 5x squared plus 0x plus 5. And you subtract. These cancel out. These go away. This is what's left right now. As soon as this is degree less than that, you're done with the division, and this is the remainder, which is going to end up being a fraction in your answer. So what we get is that this equals 2x plus 5 plus 1 over x squared plus 1. And now you can try and integrate it. This is going to be 2x squared divided by 2 plus 5x plus, this is inverse tangent, plus c. So the final answer is x squared plus 5x plus inverse tangent plus c. So all those other integration techniques are fair game. Now, sometimes this is something that you would then do partial fractions on after the degree of the top is smaller than the bottom. Then you could do partial fractions on this, not this one, but so a lot of times you are going to do partial fractions after you do long division. Okay. If you try and do partial fractions with something that the degree of the top is bigger or equal to the bottom, it might seem like everything's working out and your answer might look really close to the right answer, but it will be wrong and it does not work. So today's assignment, I'm going to try page 369, 1 to 7 all. Check your odds in the back of the book. I'll see if I put the evens online or not, but try these problems and try this new algebra technique of partial fractions. Also, long division is probably something you learn First time in Algebra 2, long division of polynomials. Synthetic division won't work with this. Synthetic division only works for dividing by binomials. This is essentially a first degree binomials. This is a second degree, essentially like trinomial. So you have to use long division. That's it. Try these out. Try the homework.